Every day, scientists forecast weather, track asteroids light years away, and map the human brain. Yet, when it comes to the ground beneath our feet, predicting an earthquake remains one of humanity's greatest unsolved scientific puzzles. Why? Despite our technological advancements, pinpointing exactly when and where the next major earthquake will strike is a challenge that has eluded us for generations. The difficulty isn't a lack of effort or sophisticated tools, but rather a fundamental battle against the hidden, chaotic, and multi-scale nature of our planet's crust. Earthquakes begin with the slow, relentless movement of Earth's tectonic plates. These colossal slabs of rock constantly grind past, collide with, or pull away from each other. Where these plates meet, or where cracks form within them, are called fault lines. Over time, these faults get stuck, preventing smooth movement and causing immense stress to build up within the surrounding rocks. Think of it like bending a sturdy stick. The energy is stored, waiting. When this accumulated stress finally overcomes the friction holding the fault, the rocks suddenly slip past each other, releasing that stored energy as powerful seismic waves. This sudden slip is the earthquake. Why is this seemingly simple geological event so uniquely elusive? The first major hurdle is depth. Earthquakes typically originate several kilometers below the surface, far beyond the reach of direct observation. We can't simply peer into a fault line to see what's happening. Instead, we rely on indirect measurements from the surface, and what's hidden is incredibly complex. Fault lines are not neat, smooth cracks. They are often intricate, fractured zones with countless irregularities, varying rock types, and even trapped fluids. Imagine trying to predict when a complex, submerged machine with countless hidden interacting parts will suddenly seize up. The stress doesn't build up uniformly, it concentrates in unpredictable pockets, influenced by every tiny bump and nuance of the fault surface. A slight variation in rock strength or the presence of water can drastically change how stress accumulates and dissipates. Another critical challenge is the absence of reliable short-term precursors. Many hope for clear warning signs that reliably indicate a large slip is imminent, perhaps hours or days beforehand. Unfortunately, such signals have proven maddeningly inconsistent. Consider foreshocks, smaller tremors that sometimes precede a larger earthquake. While they might seem like a promising indicator, most small tremors are just background seismic noise, and many major earthquakes occur without any discernible foreshock activity. There's no way to definitively tell if a small quake is merely a small quake, or the prelude to something much bigger, until the larger event actually happens. Other potential precursors, like subtle ground deformation, changes in groundwater levels, or electromagnetic signals, have also been studied. While these phenomena can occur, they often happen over long timescales, or are so subtle and inconsistent that they cannot provide the precise, real-time warning needed for an imminent prediction. It's like trying to predict the exact moment a tightly stretched rubber band will snap. You can see it deforming, but the precise point of failure, influenced by microscopic flaws, remains largely unknowable until it happens. Fundamentally, the Earth's crust behaves like a complex, non-linear system. This means that tiny, almost imperceptible changes deep underground can cascade into disproportionately large and sudden events. The forces at play operate across vast scales, from the friction between individual mineral grains to the slow, massive movements of tectonic plates. Interactions at one scale can dramatically influence behavior at another, making the system inherently chaotic and extremely difficult to model with the precision required for earthquake prediction. It's not just about knowing how much stress is building, but how it's distributed and when the critical tipping point will be reached at any given point along an irregular fault. Crucially, there's a difference between prediction and forecasting. While precise earthquake prediction, stating a specific time, place, and magnitude for an imminent event, remains out of reach, earthquake forecasting is a well-established and vital science. Geologists can assess the long-term probability of earthquakes in specific regions based on historical seismic activity, known fault locations, and the rates of tectonic plate movement. This allows us to understand seismic hazards and build structures designed to withstand future shaking, saving countless lives. So despite all our scientific prowess, the ground beneath our feet holds a powerful secret. Predicting earthquakes isn't a problem of insufficient data or inadequate technology in the way predicting weather once was. Instead, it's a profound challenge rooted in the deep, hidden, and intrinsically chaotic nature of the geological processes themselves. The Earth's fault lines are not clockwork mechanisms. They are complex, dynamic systems that resist revealing their exact breaking point. The unpredictability of earthquakes reminds us that some of nature's most powerful forces operate on principles we are still striving to fully comprehend. As our understanding of complex systems evolves, could new approaches, perhaps leveraging AI or quantum computing, ever truly bridge this fundamental gap in our knowledge?